Hi everyone, we're going to continue on with talking about some polar graphs. We're going to talk about limacons, probably a word you've never heard before. It's a French word for snail, and I think maybe you'll see why as we go through these. Before we get into the whole idea of graphing them though, I want to talk about a couple of things that are probably going to make the whole graphing process a bit easier. I want to talk about symmetry with polar equations. There's actually three different types of symmetry. You can have symmetry with respect to the polar axis, symmetry with respect to the line theta equals pi over 2, or symmetry with respect to the pole. I'll show you what each of them are. So this point right here is your point r theta. Right, so this distance is r, and this is your angle theta. So we can do three different things. We can replace theta with negative theta. We can replace r and theta with negative r and negative theta respectively, or we can just replace r with negative r. Those are the three different ways we check for symmetry. Okay, if an equivalent equation results, meaning you get back what you started with, then that's the type of symmetry it has. So with respect to the polar axis, we replace theta with negative theta. And so we'd end up with something here. So we'd still have r comma theta, right? So this would be symmetrical to our original one, symmetrical about the polar axis, okay? Symmetry with respect to the line theta equals pi over 2, if we replace r and theta with negative r and negative theta. Okay, so again, here's r theta. If I replace theta with negative theta, that puts me down here. And then if I replace r with negative r, that flips me over the pole. And that puts me here. So if I replace negative r, if I replace r and theta with negative r and negative theta, then I get back what I started with, then I have symmetry with respect to this line, theta equals pi over 2. That's my vertical line here. Again, here's r and theta. If I replace r with negative r and I get back what I started with, right, that would be negative r. So this point down here would be negative r negative theta. Then I have symmetry with respect to the pole. So you can replace theta, you can replace r, or you can replace r and theta. And depending on which one you do will tell you what kind of symmetry you have. That might seem like a lot, but let's go through an example so you can kind of get the idea of what I'm talking about. Okay, so we're going to check for symmetry, and then we're going to graph this polar equation, r equals 1 minus the cosine of theta. So let's check for symmetry with respect to the polar axis. Okay, that means we're going to replace theta with negative theta. So I end up with 1 minus cosine of negative theta. Now, cosine of negative theta, think about what happens. If these are your quadrants, and negative theta dips you down into the fourth quadrant, but cosine is still positive in the fourth quadrant. So cosine of negative theta is actually equal to the cosine of theta. It's called an even function because of that, okay? So we end up with r is equal to 1 minus cosine theta, which is what we started with. And so we can say, yes, it does in fact have polar symmetry. Okay, let's check the next one, which is theta equals pi over 2. So if I negate both, so if I replace both r and theta with negative cosine and negative theta, I end up with negative r is equal to 1 minus cosine theta. If I multiply through or divide through by negative 1, I get 1 r equals negative 1 plus cosine theta. Clearly not what we started with. So it does not have symmetry with respect to the line theta equals pi over 2. We'll check symmetry with respect to the pole. So in this case, all I do is replace r, and this ends up looking just like the last one we did. So again, that does not have symmetry. So the only symmetry I have is with respect to the polar axis. Okay, and so now what I'm going to do is I'm going to make a table, and I'm going to graph some points. Okay, I think it's easiest to do it down here, so I'll make a table down here. I'll do it this way this time. So if I have 0, pi over 6, pi over 3, pi over 2. So notice I'm not I'm doing some of the main ones because I didn't do pi over 12 or whatever, because that doesn't give me an exact value. I'm doing these because it gives me an exact value. Okay, 2 pi over 3, 2 pi over 3, 5 pi over 6, 5 pi over 6, and pi. Now, notice I'm only doing values from 0 to pi. Okay, I have symmetry with respect to the polar axis, so I don't need to do on the other side because I'm going to be able to get the points on the bottom here. Okay, so when theta is 0, I end up with 1 minus 0 or 1. When theta is pi over 6, I end up with 0.13. Now, this is all stuff that you can do in your calculator. You can just plug these values into your calculator to get them. So don't worry about having to be exact as far as, you don't have to put in the roots and all that stuff, because you can get a decimal approximation for the roots. Okay, and we have 1.5. I have 1.87. And I end up with 2. Okay, so I'm going to go ahead and plot those points. Now, because I have all these decimals, I'm actually going to stretch out my r value. So instead of the first little circle here being 1, I'm going to put 1 out here, and I'm going to put 2 out here. So every one of these circles is half of a unit, just to make it bigger so it's easier to see. Okay, so when theta is 0, r is sorry, r is 0. That should not be 1. That should be 0. Okay, so when theta is 0, r is 0. When theta is pi over 6, pi over 6 is here. I'm at 0.13, so I'm somewhere right around here somewhere. A small little point in there. At pi over 3, I'm at 0.5. At pi over 2, I'm out here at 1. At 2 pi over 3, I'm at 1.5. At 5 pi over 6, I'm at 1.87, so I'm right about here. And then at pi, I'm at 2. Okay, now again, remember I have polar axis symmetry, so I'm just going to plot these same points on the other side of my pole. Okay, so here I'd be down here, I'd be just shy of 2, and then at 4 pi over 3, I'd be at 1.5. 3 pi over 2, I'd be at 1. At 5 pi over 3, I'd be at 0.5. Whoops, right here, 5 pi over 3. And then at 11 pi over 6, I'd be in here like that. So the graph that I end up with is this. And it looks kind of like this. Oops, wrap that around like that. And you see there's kind of like a little, it kind of squeezes in like that. Okay, so that is our limacon. That's our first one. Okay, so that's what it would look like. Okay, that's what the graph looks like. That's the process you want to go through when you are doing these. For the next one, what I would like you to do is I'd like you to pause the video, check the symmetry on your own, see what you come up with, and then you can start the video and I'll have the answers posted here. Okay? Okay, so hopefully you got the symmetry done and you may or may not have continued on and made a table, but that's okay if you didn't. Let's talk about the symmetry. The symmetry for all three of them was no. Now, here's kind of the stickler to that. Because when it says yes, then you know for sure it has that symmetry. When it says no, that means it may or may not. Sorry, I think I had to sneeze. It may or may not have that type of symmetry. So when you see no, that doesn't guarantee that it doesn't, but when you see yes, it means that it absolutely does have that kind of symmetry. Okay, so I didn't connect the dots here, but what I did was I made a table all the way from 0 to 2 pi. I just broke it up onto two lines here. And again, if you notice, I didn't put any multiples of pi over 4 in my table. The only reason is because we're dealing with sine and cosine, and that's always going to give you a decimal. So there's no need to really add those other points in there. You can if you want to, but you don't need to. The reason I stick to multiples of pi over 6 and pi over 3 is because one of them is always going to be 0.5, and that's really easy to graph. So, or some form of 0.5 and then multiplied by something else is always going to give you either a whole number or a half of a number. So that's why I stick to those. If you want to put in multiples of pi over 4, you certainly can. If you notice, so this first row, let me just connect those dots. I plotted those. And I started here at 1, and then it goes around like this. And it comes up and around like this. So that is that first row of the table. If you go down to the next row of the table, okay, at 7 pi over 6, I'm at 0. So I come around like this to here. Oops. Get my pen to work. It comes around like this. And then at 4 pi over 3, I'm at negative 0.73. So 4 pi over 3 is down here, but the negative flips me over the pole. Okay, so that's why these three dots here are above the polar axis, because these three numbers are negative and those flip us over the pole. So what happens is we end up with this inner loop, and that's what our graph looks like. Okay, this is called a limacon. Like I said, it kind of resembles a snail almost. That's why they call it that. And depending on the equation itself, so all of our equations are either going to be r is equal to a plus a plus or minus b cosine theta, or a plus or minus b sine of theta. Okay, so all of the ones that are cosine are left and right. You'll see here's cosine, here's cosine, here's cosine, here's cosine. You'll see they're symmetrical to the polar axis. And the ones that have sine in them, that's this one, this one, this one, and this one, all are symmetrical to the line theta equals pi over 2. The plus keeps it on the positive side, the negative moves it to the negative side. And when you have an inner loop, that specifically happens when A is less than B. So that scenario gives you an inner loop. Okay, and then quickly, just to wrap it up, these are the different forms of those. You might have a convex that's almost kind of flat on one end. You might have a dimple. This is called where it buckles in at the origin. That was the first example we did. That's a cardioid. And or cardioid, and then you also have an inner loop. That's it, everybody.